好，同学，那个我知道现在好像，其实好像人也还没有很多，呃，好像哦，也已经9点了，那我们就开始哦，OK，那few things to talk about, OK，before we start, OK，呃，first，I apologize for the, you know, having to move the course to like today, okay, and do it online because I will be out of country for a conference next week. OK，先跟大家说声抱歉哦，需要改时间了，改到线上了，因为下礼拜我人不在台湾哦，那个实在是呃没有办法哦，那个那 second OK，嗯，I need to tell you that yeah uh I'll give you supposedly like we have like the first lecture the previous lecture like is not covered by the quiz. So previous lecture and this is the if we exclude the midterm, OK，我们如果说不看期中考，OK，上一堂课就是期中考之前的一堂课，OK，the class before the midterm and this one, OK, will be enough for the quiz, OK. Um, so what happens is that I'm going to give you practice questions um, later today, and we will have a quiz. Okay, the fourth quiz. Okay, uh, in class. Okay, uh, which will be held like in regular hours. OK，就是在课程快要结束的时候，我们会有第4次的小考哦，下一次的上课。However, OK, after I check the calendar, OK, I found that OK, um, the next lecture is going to be not the next week, but the next week. Well, not the next week, but the next week. Okay. Let me explain. Okay. I'll be out of country next week. That's why we have a class today, right? I mean, originally I thought we will have quiz next week, but if you look at the calendar, okay, calendar. Where's my calendar? So this is my calendar, and obviously we are here. Okay, 25th. Okay, today. I mean, which is supposed to be a holiday. Okay, so this is another reason I need to apologize. Okay, um, but you know, as I said, like so I will be out of country next week. So um, shall not be um, available, okay, um, this day, okay. So on the 29th, okay. But when I look at the calendar, okay, I thought originally I thought like we will have like a quiz today, okay, not today, like on the November 5th, which is the first lecture in November. But obviously, you see that November 5th and November 6th, okay, will be the field day, okay, field day for our university, OK，就是11月5号跟11月6号是我们的全校运动会哦。那 because of the field days, the class, all the classes are off，所以礼拜3跟礼拜4的所有的课都会停掉。OK， so in other words, OK， the next time we will have the lecture, OK, you know, will be November 12th，就是下一次我们真的会有课的时间，其实是11月12号，OK, from 9, so from 9 to 12, obviously. So, as I said, OK, I will give you like the fourth quiz near the end of the class on November 12th. So you have like quite a long time to prepare for this fourth quiz. In other words, okay, the format will be similar to the previous one, okay? I will give you a little bit more problems, okay, to uh, practice, okay, in the fourth quiz, because it's not like exactly 2 weeks. It's, you can say it's almost 4 weeks. Uh, okay, anyway, back to uh, the slide. So, okay, the last point to mention before we start the class, okay, um, as you may have found out, um, I'm still, what happens? Okay, oops, okay. Okay. As you may have found out, I'm still coughing. I got a cold like from my trip to Vienna. So it has been like uh, close to 2 weeks. Okay, and um, I because uh, this week in China we had too many activities, so it is difficult for me to recover from my cold. Okay, um, and because of my sore throat. Okay, my voice is a little bit low. Okay, um, I understand like doing like a online class under this condition may not be ideal. Okay, but uh, well, that's we really have to do it. Okay, uh, so anyway, uh, so let's get started. So um, we have learned, okay, uh, we can represent a linear transformation by matrix, okay, and also this linear transformation, okay, is with respect to a certain basis, okay, and then you can consider, you know, switch, I mean, represent the same linear transformation using different bases, okay, uh, and there's some relationship, okay, that is illustrated in this figure, okay. For, for example, if you have a linear transformation from V to W, okay, um, that will move you from base 1 to base 2. So this is LB1, B2. Okay, you have a matrix for that. Okay, you can do the same thing by first applying a coordinate transformation from base 1 to base 3. So we can apply this TB1 to TB1 to B3 first. And then, okay, apply this linear transformation from B3 to B4. Okay, and then you know, uh, you know, transform the coordinate back to B2 from B4. Okay, so TB4 to B2. Okay, so you can do something like this, which will have exactly the same effect as LB1, B2. Okay, so if we represent the matrix, all these things by matrix, say LB1, B2 is matrix M. Okay, and this linear transformation, this coordinate transformation from B1 to B3 is A. This the same linear transformation from B1, B3 to B4 is B. Okay, and this one, okay, the transformation of coordinate from B4 to B2 is C. Then this M, LB1 to B2, will be, you apply A first and then apply B and then apply C, right? So if we look at the matrix, it's going to be in, if you write it down, it'll be M equal to CBA. Okay, because on the you are going to apply to this thing to a column vector on the right hand side, right? So if it's CBA, then you apply A to that column vector first. Okay, so you move that column vector from base 1 to base 3, and then B, okay, you apply B to the resulting coordinate, okay, to here, and then you apply the C, okay, to move it back to the coordinate B2. So obviously there are a lot of like possible like routes in this figure, okay. So this is like something you have to remember, okay, and we will make use of this uh, today, okay. So here's a theorem, okay. U, V, and W are vector spaces. B1, B2, B3 are bases of U, V, and W, respectively. Okay, so L1, U2, V, okay, and so L1 map from U to V, L2 map from V to W are linear transformations. Okay, then A be the matrix representation of L1, and the B1 with respect to B1 and the B2. Okay, and the B be the matrix representation of L2 with respect to B2 and B3. Then you can also do like a kind of like a linear transformation concatenation. Okay, so you transform a vector, okay, by using L1. Of course, that vector must belong to U. Okay, must belong to the vector space U. Okay, so after you map that vector by using L1, it will be mapped to a vector in vector space V. Okay, and then you apply L2, okay, to that vector. So yeah, I mean, it will be mapped to obviously somewhere in W. Okay, so here we want to show this combination, this composition, L1, L2, L1. Okay, um, in the order it should be you apply L1 first and L2, right? But when you write it, okay, obviously, it's going to be L2, okay, and with a little circle and L1, okay. So it's a composition of two linear transformation, and we want to show that this is a linear transformation, okay. So what is linear transformation? I know, like we have like a midterm a week, well, not a week ago, actually 3 days ago, right? On Wednesday. Oh, by the way, how do you think about the midterm? Is it reasonable? Okay. Um, I think like we should be able to give you the grades, okay, the next time in class. okay, which is actually like a November 12th. Okay, November 12th. So I really hope to uh I mean look forward to learn like performance of your midterm, okay, after we finish the grading, okay. Um, so what is linear transformation, by the way? Let's go back. This is like the main thing of this chapter, right? So if you can show L, L okay, AU plus BV will be ALU plus BLV, okay, then it is a linear transformation, right? So, how do I, let me see if I, so it's L1, L2, okay, and then we have AU plus BV, right? Okay, and eventually what we want to show is that we have A L1, L2, U plus B L1, L2, V, right? So this is our eventual goal, right? Eventual goal. If we have that, we prove this theorem, okay? So let's give it a shot. Don't know how to. Okay, what happened? Where are we? Hmm? 为什么回不去？Okay, so okay, finally. So L2, L1, AU plus BV equal to L2. We apply L1 first. So it's going to be A L1 U cross B L1 V, right? And then it's going to be, if you look at like each term separately, okay, it's going to be, you apply L2 again. It's going to be A, because remember L1U and L1V, they are both vectors in the vector space V. Okay, so you can apply L2 to them. Okay, so it's going to be A L2 L1 U plus B L2 L1 U V, sorry. So that's it. Okay, and then you basically need to argue, okay, this is the same as L2 L1, okay, U is going to be the same as, you can treat like L2 L1 as one operation, okay, then pretty much that's it. And the matrix representation of L2 L1, okay, with respect to B1 and the B3 is BA, okay. This is similar. The argument will be similar, okay. Let me, instead of using L1, L2, write that into L1, L2. Basically, now you just write L2, the linear transformation of L1 and L2 by the matrix. So the L2, L1, AU cross BV is going to be, L2. We know the matrix representation for L1 is B1, right? Sorry, B2. Sorry, B2, B3 are bases. So it's A. What am I talking about? AU cross BV. So then obviously it becomes L2 B, sorry, A, capital A, U cross B, capital A, V. Okay, and then you can represent L2 by using the matrix B, right? So it's going to be B, you apply B to A, U cross B, A, V. Okay, so it's going to be A, B, A, U cross B, B, A, V. Okay, and this one will be exactly just like a B, A, A, U cross sorry, AU plus BV. And also, if you look at the matrix in another way, it's going to be A, BA, U, okay, plus B, BA, V. So the matrix representation of L2, L1 is BA. Okay. It's not very easy to write proof, okay, in the online class, okay. We are out of like a Blackboard. Well, online, actually, we have Blackboard online, but the Blackboard is not as convenient as what we have like in class, okay. So okay, where am I? Proving the theorem, right? How come I suddenly lost where I am? Here. So there are a few uh, linear transformations we could consider, okay, when you do like computational geometry, okay, because in computational geometry, we always need to, somehow like, I mean, we always need to calculate like the for example, like dilation, contraction, reflection, you know, rotation, translation, we want to do all these actions through matrix multiplication. Okay, remember I told you matrix multiplication is pretty much linear transformation, right? So if you can use like um, matrix multiplication to deal with like these actions, you know, to certain object, okay, to certain vector, okay, in three in a two-dimensional space, it'll be very convenient. Okay. So first is the dilation, the contraction. Okay. Lx equal to Cx. This is a very easy one, right? It is obviously a linear transformation, right? Uh, um, and so whatever uh, the vector, size of the vector, you just enlarge it by the size of C. Okay, so obviously when C is greater than 1, we call it dilation. If C is smaller than 1, we call it contraction. Okay. And because we want to represent this, okay, as like a matrix. So what is the shape? What's this matrix look like? Okay, for this operation. Think about this. Okay. You represent this one by consider the basis. Okay. In a two-dimensional space, you have like that we can consider the easiest basis, E1 and E2, right? So if you put E1 here, okay, it becomes C times E1, right? So you'll be, you know, if you write it as like the basis, the linear combination of bases is coordinate is going to be C0, right? So in other words, the first column is going to be C0. And then the second one, E2, you apply E2 to here. Again, E2 is enlarged by C times, and you do not have any component for C for E1. So it becomes 0. You write it in, column vector. So this is the matrix that represent this Lx equals Cx. Okay, you can imagine if you multiply any column vector by this matrix, you are going to enlarge the matrix by C times. It's very easy, right? How about the other actions? Refraction. Refraction, it is about a certain axis. Okay. You can reflect, you know, uh, with respect to x-axis. You can reflect with respect to y-axis. So it's up to what you want to do. Say, you want to, let's just discuss one case. You want to do a reflection about x-axis. So this is x-axis. This is x-axis. So in this case, okay, whatever happens here will be reflected here, right? Right? So same thing. Okay, you consider E1 and E2. E1 has the same direction, okay, to this x coordinate x axis. So if you put E1 here, okay, it is still going to be E1, right? So the matrix, okay, the first column in the matrix should be 1, 0. How about the Y? If you have like E2, okay, after reflection, it becomes exactly the opposite, right? So what happened for E2 is it's going to be the negative E2. So it's going to be 0. -1. So this is the matrix for the reflection about x-axis. You can certainly consider the reflection about y-axis. Okay. How about rotation? Say you have a vector. Okay, you rotate theta degree. Okay, you want to represent rotation. We already know rotation is a linear transformation because we discussed this earlier. Where is it? I believe like earlier. Here. This is actually the matrix representation of the rotation. But why? Let's again think about here. Okay. Say we have a E1. Okay. After the theta degree become like this, right? And this is your theta, right? So if you consider the, the x projection, it's going to be cosine, because E for the vector E, the length is 1, right? So 1 times cosine theta. So it's, well, the first color is cosine theta. And the height, okay, is going to be, this one, which is sine theta. How about E2? If E2, is, changing to by theta degree, okay, then you look at here. It's a x, the projection is a projection to x coordinate. This one, okay, is going to be sine, okay, theta, but it's on the opposite direction, so it's going to be full negative sign. Okay, negative sign. Okay, and then its y projection is going to be cosine theta, it's still positive. So that's your matrix representation of the rotation. And you can combine these actions together, okay, obviously. So for the translation, okay, we know like, we do dilation, contraction, reflection, rotations, quite often, like in geometry computation, okay? geometry like manipulations. Okay. However, we also do translations, but we know like Lx equal to x plus a. That is like usually what we call translation. You move the your vector, you know, a amount by a sorry, by a you translate your uh, vector by this amount a. Okay, that is what we call translation, but it is not obviously not a linear transformation. Okay, why? Why do I say it's not a linear transformation? Okay, you know, for any linear transformation, it must transform zero vector to zero vector. Okay, to start with. Okay, I mean, if you put L0 there, it's obviously not zero. Okay, it's going to be A, right? I mean, unless A is zero, otherwise, no, L0 is not a zero. Okay, um, plus, okay, you can verify something, I mean, this similarly by using like a linear transformation definition. So we know like this translation, okay, is not a linear transformation unless like the, you know, the A is zero. But if A is zero, it means we are not transforming, right? We are not doing any translation. But it creates a problem, right? It creates a problem because remember, the purpose of for us to discuss all this is so that all this geometry manipulation can be done by matrix multiplication, right? But now it's you know, if the translations cannot be represented by linear transformation, obviously, you know, there's no simple matrix that represent such translation, right? So you cannot like do this computational geometry easily by using matrix multiplication. Can we do something better? Okay. Actually, there's a concept called homogeneous coordinate. Okay. In the homogeneous coordinate, okay, what happens is that, okay, you you try to represent your two-dimensional object by three dimension. Okay. So let's talk about like this I mean, if you want to represent transforming for example like xy, okay, so you have an extra dimension, okay, and then in the third dimension, okay, you can, you know, represent your translation. Say you want to move your object two unit, to the positive x direction, and the 3 unit to the positive y direction. Then say your object original coordinates x, y, you will, add a 1 as its third, a component. But this one is not going to, you are not going to really draw it, because we just represent a 2-dimensional object on 3-dimensional. 2-dimensional object on 3 by using 3 dimensions. So what we really are going to use is the first 2 components. So if you look at here, you will find that the result, okay, is going to be, x, sorry, this is x plus 2, right? The second part is y plus 3. The last one is still, remains to be 1, okay? So we somehow achieve our translation. We are able to represent our translation by using one extra component. Okay, and we are able to represent. So in some sense, we can say translation would be a linear transformation in homogeneous coordinate. Okay. Then you may ask, how about the previous like a dilation, reflection, like a rotation? What happens to them? Can we represent this in homogeneous coordinate as well? It's really, really easy, okay? For example, okay, for this one, basically, it's going to be, you just add one more component. The only extra is 1 here. So you can try, okay, you multiply this by any xy1, you get cx, cy, and 1. Okay, as I said, you can ignore the third component, so you got your cx and cy. Okay, so this, so you just write this one in the upper left corner, and the other part, okay, you just fill out like 0, okay, with the last like a element in the diagonal to be 1. Okay, same thing can be said to like reflection and the coordinate, like rotations. Okay, so all this can be, represented, okay, properly in the homogeneous coordinate. Okay, so that's it for this chapter, I believe. Oh no, okay, we finished the section 2. Okay, my bad. We still have the section 3. Let's take a 10-minute break. we'll come back. We'll continue the discussion of section 3. Okay. Okay. So let's continue. Okay. The next section is similarity. Okay. 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 First is the definition. Okay. We say A and B, okay, two n by n matrices. Okay. We say they are the B is similar to A if there exists a non-singular matrix S such that B equal to S inverse times A times S. Okay. Um, First, okay, I would like to, you know, uh, 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 point out that, okay, if B is similar to A, then A is also similar to B. Why? Because look at this formula, B equal to S inverse AS. Then obviously you can write A equal to S B S inverse, right? So, so in other words, okay, there exists a non-singular matrix S inverse, okay, that make A similar to B. Okay, so this is like, what should I say, like, this is like, you know, uh, if A is similar to B, B is similar to A. Okay, an example is given below. Okay, A, B, U, and U inverse are given like that. And B equal to U inverse A, U. Okay. You could certainly like try to calculate this for verification. But the more important thing is this similarity concept, okay, has something to do with like linear transformation and the transition matrix. Okay, basically, V is an n-dimension vector space. Okay, and L, say we have a linear transformation from V to V. Okay, and the B1 and the B2 are bases of V, and S is a transition matrix from B1 to B2. Okay, coordinate transformation. Okay, let A be the matrix representation of L with respect to B2. B be the matrix representation of L with respect to B1. Then we have B equal to S inverse AS. What are we talking about? Okay, look at here. S is a transition matrix from B1 to B2, right? So you convert the matrix, convert the coordinate from B1 to B2, and then you represent, you go through this linear transformation, okay, you know, with respect to B2, and then you move it back to B1, okay, by using S inverse. So this is exactly This one. You can modify B1, B2 here as B1, B1. And this B3, B4 here as B2, B2. Okay. Then your LB1, B1. This is LB2, B2. LB2, B2 is your A. LB1, B1 is your B. Okay. So B is going to be, you go here, so the transformation from B1 to B2. Okay. This is your S. Okay. S, A, and then this one is S inverse from B1 to B2, B2 to B1. Okay. So of course the order should be, because you apply this one first and then this one, this one. So it's going to be S inverse on the left. On the left, it's going to be S inverse, and then it's A, and then it's S. Basically, I mean, what we are talking about in this theorem is exactly what we already know, okay, from that diagram, okay. So one interesting example is the differential operation on P3. Okay, so if we have like we represent this D, okay, uh, by two different bases. B1 is x3, x to the power 3, x to the power 2, x and 1. The very simple one. The B2 is 2x minus 1 to the power 3, 2x minus 1 to the power 2, 2x minus 1 and 1. We want to find the A, B, and transition matrices for B1 to B2 and B2 to B1, and verify the similarity of A and B. So most of these are pretty easy, okay? Luckily, like we have slides to help me. I mean, so I don't need to write it, okay? So you consider this is your B1, okay? You try to apply your differential operation on B1 and get, like, this is the first base, okay, x to the power 3, all the other are 0, okay? And the differentiation of x to the power 3, you get 3x2, 3x to the power 2, okay? And so if you write it using like the basis 1, so it's going to be 0, 3, 0, 0, okay? How about x squared? Okay, if you differentiate x squared, you get 2x. So this is the result. And the x, okay, if you differentiate x, you get 1. So this is the result. And for 1, you differentiate 1, you get 0. So this is the result. So, if you want to represent this differentiation operation by using a matrix, it's going to look like this. Okay, so far so good, right? How about if you want to represent the same differentiation by using the B2, then the 1 here represent 2x minus 1 to the power of 3. Okay, and I hope you guys remember what you learned from your calculus. It's going to be 6 times 2x minus 1 to the power of 2. So it's going to it's going to be like this. And this one, you want to differentiate 2x minus 1 to the power of 2. So the result is going to be 4 times 2x minus 1. So you can represent it like this. The third one, okay, you want to differentiate 2x minus 1. Okay, and you get 2. Okay, so it's going to look like this. The last one, you want to differentiate 1. You get 0, so that's the result. So if you write everything into one matrix to represent differentiation for the basis of B2, it looks like this. How about the transition matrix? You want to transform the coordinate from B2 to B1. The transformation of coordinate from B2 to B1 is quite easy, okay? You consider, again, you consider every basis, okay, of B2, okay? And it's, for this one, it's 2x minus 1 to the power of 3. You expand it, it's going to look like this, right? So obviously, this one, if you write it as like the first basis, is going to look like this. Okay, the second one, okay, expand it, it looks like this. Okay, the third one here, okay, you can directly write it as like this. The fourth one is just the same. So if you represent from B2 to B1, it's going to the transformation transition matrix is going to look like this. How about you want to transition from B1 to B2? It's a little bit complicated, but it can be done. Okay, so x to the power of 3, you have to write it from the first term, 2x minus 1 to the power of 3. Try to get x to the power of 3 from here. Okay, obviously you need like a 1 over 8. Okay, to start with to get x to the power of 3. For the other terms, you try to eliminate that by using the other term because the other term do not have x to the power of 3. Okay, so you use this one to eliminate x to the power of 2. So you use this one to eliminate x, and then finally you use this one to eliminate the constant term. Okay, so you get this. And the second one, third one, the fourth one, I will not go into the detail, but it's a similar process, a little bit more complicated. But when you write it in the matrix, it looks like this. And by the way, we know that these two transition matrices, they should be inverse to each other. Okay, you can for this one you can give it a shot and try to calculate it, but it's because it's 4 by 4, so the calculation takes some time. Okay, and then the most important thing is, okay, now we have like db2, right? db2b2 is this one. This db2b2 is going to be um, um, this um, you have this one first, tb2 to b1, and then you apply this db1b1, and then finally you apply tb1b to b2. Okay, or in another word, um, if you allow me, okay, I'll just omit the B, okay, just two just here, D underscore two just represent like this uh differentiation operation, okay, uh you know uh you know with respect to like base two, okay. So this is from one to two, okay, times, okay. So differentiation operation represented by base two will be, you know, you the last one, you do like a transition, use transition to bring the base two to base one, and then you apply the same differentiation, but now with base one, and then you move the coordinate back to base two, so it's T1, 2. Obviously, this is also hold, okay? This equation is also valid, okay? And we learn all this actually from this diagram already. So this is really nothing new, okay? So that's it for this chapter, okay? So we are done with this chapter, and now we move on to to the um, the chapter 5. Get rid of this. orthogonality. So this one, we have 7 sections, okay, in this chapter. But luckily, the section 1 is really real easy. Okay, scalar product in Rn. Why do I say that? It's because this part is about what you learned in high school. Okay, so if we have a U, okay, and a V, vector U and V and W, okay, in Rn, and the 2 scalars C and V, then the length of U, length of V denoted by, this V with like absolute value or like norm. Okay, actually it's like we call it norm of V. Okay, is U1 V1 plus V1 squared plus V2 squared plus blah 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 plus Vn squared. Okay, and then you get a square root of that. Okay. It is also called as magnitude or norm. Okay. As I already say, we usually call it norm. Okay. Some people also call it magnitude. Okay, or size. Okay. So if the size or the norm of V is 1, then the vector V is called a unit vector. Okay. So we have several theorems. Okay. For example, C times V, and the norm of that is going to be C, okay, the absolute value of C times the norm of V. Okay. This should be very straightforward because like a CV, basically like all the component in V is multiplied by C, right? And then, when you do the square, okay, the C square can be extracted from every component. And then because it's a square root, so the result is going to be C to the power absolute value of C times the rest. The rest will be the norm B. Okay, so that's like very straightforward. So if B is a non-zero vector, then 1 over the norm V times V is a unit vector and has the same direction as V. Okay, first, it's a unit vector. That's very easy to verify because like, you try to calculate the norm of this one. Okay, the numerator and denominator cancel out each other. So it's going to be 1. Okay, which will, according to the definition, okay, it's a unit vector. Okay, and it is pointing to the same direction. Okay, because like we multiply V by a number, right? By a scalar. Okay, and also this is not just any scalar. This has to be positive. Okay, so we maintain the direction of V. Okay, but why is it positive? Because 1 is positive, obviously, and none of V because it represents the size. Okay, it has to be positive too. Okay, or look at the definition. The norm V is a result of the square root, so it has to be positive. So this guarantee that is the whole thing. I mean the v times this one, okay, maintains the direction of v, okay? And the Euclidean distance between two vectors, u and v, is duv equal to u minus v, okay, no. This is also like very easy to show, okay? The duv, okay, first u minus v is like every component, subtract. I mean the subtraction of every component. Okay, so each component u1 minus v1, u2 minus v2, and so on. So none of that will be u1 minus v1 to the power 2, and then plus u2 minus v2 to the power 2, and so on. Okay, and then you get a square. That's pretty much just how we calculate the distance of two vectors. Okay. And then it's a dot product, okay, or what we call inner product. Okay. So as I said, like you must have learned this from high school. So the dot product of u and v is denoted by u dot v and given by u dot v equal to u1 v1 plus u2 v2 blah, 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 plus u1 vn. And if u and v are written as column vector, then u dot v is u to the power, I mean the transpose of u times v. Okay, so this is like very easy to understand. And then we have the following properties. Okay, u dot v equal to v dot u, u times u dot like v plus w. Okay, we have like distributive law. Okay, c times u dot v equal to c times u, okay, first, and then dot v. I mean, this is like very easy to verify. Okay, and u dot u equal to u, the norm of u square. Okay, and u dot u greater or equal to 0. Okay, and u dot u has to be 0 if you know, if you want u dot u to be 0, then u must be 0. Okay, this is in fact only if. Okay, because u dot v, u dot u basically represent like a square of norm. Okay, if it's 0, okay, well, it has to be, the case that like the size of u is 0. So as I said, you learn all these like property from high school. Then it's a Cauchy-Schwarz inequality. Okay,这个叫什么？高斯不等式是不是？Okay, in high school，在高中的时候，OK，我记得高中的时候，你大概就是怎么证明这个东西，就说，哎，你因为 u 大的 v 会等于那个 u 的 norm 乘上 v 的 norm，或者 u 这个 u 的大小乘上 v 的大小乘上 cosine theta，那因为 cosine theta 这个值是介于0到1之间嘛，所以这个东西一定是这事实一定满足哦，所以那个就这样子。因为高中的时候大概就这样，但是问题来了，就是说我们还没有定义 cosine u 大的 v 等于 uv 的那个弄的乘积再乘上 cos 这样，我们还没有这个，那怎么乘？就我们定义哦，这个一个特别的向量，我们叫它 y 向量等于这个 u 向量除上 u 的 norm 减掉 v 向量除上 v 的 norm，这没有问题吧？就是 u 的向量嘛，我讲除上 u 的 norm 就是乘上 u 的 norm 分之一啦。对，那另外也是一样，就这个当然 u 是一个u 除上 u 的弄是一个向量，v 除上 v 的弄是一个向量，然后两个相减当然也是一个向量，对不对？然后我们知道说 y 大的 y 要大于等于零嘛，对不对？这个我们知道，从前面的讨论就知道了嘛。前面我就不翻到前页去了，你们知道的。翻过去要再重新搞一次，我就懒得翻了。那 y 大的 y 是什么东西？就是这个，对不对？u 你知道 y 大的 y 就等于这个东西嘛，对不对？这没有问题吧？就是它的这个里，它的这个，按照这个 y 写出来，它的弄的平方嘛，它的平方。那这是什么？我们可以展开，对不对？所以呢，这边就 u 大的 u 除以括弧 u 的平方，对不对？对，这是第一项，对不对？就这个东西的这个 u 大的 u，然后除上那个 u 的那个弄的平方，那上下就 cancel out 了，对不对？中间是 u 大的 v 除上，对不对？加上类似像第一项的 v 大的 v 除上 v 类似像这样的嘞。那第一项跟第三项都是一嘛，对不对？所以变2减掉2倍的 u 大的 v 除上这个刮弧，这没问题。那我们知道这个东西呢，大于等于零，对不对？对不对？所以呢，我们把它移过去，这个移过去，两边除以2，所以我们就得到一会大于等于 u 大的 v 除上 u v，对不对？对不对？或者你可以推出来说，这个乘过去，对，我们就得到这个东西。这样可以吗？所以这个是那个 culture inequality 用另外一种方法来证明哦，就是因为我们不能够定义，就用 cosine theta，因为 cosine theta 还没定义。好，那 anyway，那我们接下来就有定义了哦，angle between two non-zero vectors u and v，我们就可以算，就是说 u 大的 v 除上 u 的 norm 乘上 v 的这种 norm，是它的 cosine theta。OK，那 two vector u and v are orthogonal，代表说这个两个的这个 inner product，这个两个乘起来是零嘛？OK，那这种情形的话，那 cosine theta 等于零的情形，当然 theta 就等于什么？等于90度啊，或者就等于等于二分之派了，二分之派。嗯，好，所以 OK，另外一个公式哦，另外一个定理啦，这个东西就更简单哦，就是 triangle inequality，就是 u 加 v 的这个 norm 会小于等于 u 的 norm 加上 v 的 norm。那这个很显然哦，这个，我想不用证明哦。这个你看说 u 的那个 vector 加 v 的 vector，就是你等于说这个它结果就是 u 加 v vector 就是下面这一条嘛，因为三角不等式哦，就是斜边哦，就是任何一边会小于两个边的那个和哦，所以 u 加 v 的这个边的大小会小于 u 的大小加上 v 的大小。OK，唯一会等于是说什么？三个这 u 跟 v 在同个方向，那 u 加 v 就刚好叠加上去了。那这个是会让它相等的那种情形。可以，然后最后就是那个毕氏定理啊。Pythagorean 这个 theorem 就是毕氏定理。那 two vector u and v are orthogonal if and only if u 加 v 的 square 会等于 u 的 square 加上 v 的 square。OK，那这个也是很简单哦，因为 因为 u 的 square，u 加 v 的 square，事实上会等于呢 u 加 v inner product u 加 v，那这会等于呢对 u 大的 u 加上2倍的 u 大的 v 加上 v 大的 v，这会等于呢 u 大的 u 就是 u 的，对不对？那但是呢，我们因为为什么中间那一项不见了哦？因为中间那一项呢，我们知道 u 大的 v，如果它是那个 orthogonal 的话，u 大的 v 是0嘛，所以这中间这一项就不见了。那 u 大的 u 就是 u 的这个 square 哦，这个 u 的弄的 square。同样道理，v 大的 v 也是 v 的弄 square。所以呢，我们就知道说 u 加上 v 的这个 square 会等于这样子。OK，所以这个也蛮简单的哦。所以那不能够，所以我们先休息一下好了。我们先休息个10分钟哦，那回来我们再上最后一堂课。 Okay. Okay. So, um, we can also talk about the projection. Okay. If U and V are vectors, we have V equal to V plus V1 plus V2 for some unique V1 and V2, such that the V2 dot U equal to 0, and the V1 is C times U. So, so it's like V1 is the V's projection on U. Okay, so it's V1 is like a U dot V, okay, divided by square, the square of U's norm, okay, times U. Okay, first we know what should I say, this is U, this is V. The projection of V on U, this is your projection of V on U. Okay, and obviously, if this is theta, and this size will be, you know, um, the V cosine, right? V will be the size of this one times cosine theta. Okay, so size of this one is size of the V will be, just normal V. Okay, and then cosine theta. Okay, that's supposedly what you have here. But cosine theta, um, we don't have cosine theta, right? So it's like V, we have um, U dot V divided by U V according to the definition of cosine theta. And then, okay, uh, the V and this V cancel out each other. So we have a U dot U, a U dot V divided by U. Okay, so that's the size of this one. And because this is size, you need a direction, right? Direction, if you want a direction of a vector, then it's U divided by the known U. Okay, so that's why, okay, we have U dot V divided by U times U divided by the known U. So that's why we have two, square, we have root, the root is a square, okay? And the size of this projection is this one, right? Alpha U dot V divided by the known U, okay? So So that's it for the first section. And then we can talk about the orthogonal subspaces. Okay. So that S1 and S2 be two subspaces of V. If each vector, okay, V, okay, can be uniquely written as V equal to S1 plus S2, where S1 is from S1 subspace, S2 is from S2 subspace. Then V is the direct sum of S1 and S2, and you can write V equal to S1. We say this is direct sum S2. Okay, so as an example, this is actually a basis. Okay, this basis actually span R3. Okay, R3. So obviously, the first vector, okay, the span of first vector, we call it S1. The span of second and the third vector, we call it S2. So obviously, because this is a basis of R3, so any vector in R3 can be written as a linear combination of these three bases. In other words, any vector can be written as you know uh, S1, okay, which is like a constant times the first basis, first vector, plus, okay, the linear combination of the second and third basis, which is belong to S2. Okay, so this is obviously the case. Okay, then this is the exercise. Okay, but this exercise is a little bit complicated, so I would just give it to you. Okay, let me. Is it? Okay, if V is an n-dimensional vector space and V equal to S1, direct sum S2, okay, prove that the dimension S1 plus dimension S2 equal to n. So first, let U1, U2, U K be basis of S1. V1, V2, V M be basis of S2. Okay. So in other words, let's assume, in other words, so we know like dimension S1 is K and dimension X2 is M. So now we want to show that K plus M is N. Okay. So first, we need to show First, when you show any V in V can be written as S1 plus S2, where S1 in S1 and S2 in S2, right? This is like a definition of direct sum, right? So, in other words, we know like this S1, this vector S1, vector x1 can be written as a linear combination of u1, u2, blah, blah, uk, right? And S2 can be written as a linear combination of V1 to Vm, right? So in other words, we know like this linear, I mean, any vectors can in S can be written as a linear combination of ui and vi. Okay, so in other words, the combination of these bases span S, sorry, span V. Okay, so that's the first thing, right? And also, if you have here, if you have any vector that can be written as like a linear combination of ui and vi, so it's like a u1, a1 u1 plus a2 u2 plus da 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 plus a k uk plus so any vector can be written as like this plus b1 v1 plus b2 v2 plus zeta plus bn vn, right? According to our you know uh, what we know here. So obviously this works for when V is zero vector as well, right? This work for when V is a zero vector as well. So when, in particular, when V is a zero vector, you can move all the term related to U to the other side. So in other words, negative A1 U1 minus A2 U2 minus minus AK UK will be B1 B1 plus B2 V2 B2 V2 plus plus Bn Vn. Is that right? So in other words, okay, this part tells us that, okay, the left-hand side, right-hand side are the same. And the left-hand side belongs to S1, right? It's a linear combination of the basis of S1. The right-hand side is a linear combination of basis of S2. So a vector in S1, okay, equal to, well, a vector, so what I'm telling you is that, okay, this vector, okay, when it is in S1, it is also in S2. But okay, the S1, S2 are two subspaces. And when you have direct sum of S1, S2, the S1, S2, the intersection is zero. Is empty. Okay. Let me correct myself. The intersection is a zero vector. The intersection must be zero vector. Why? Think about this. If you have a vector that non-zero vector that is in the intersection of S1, S2, then obviously you can write that vector, uh, as as S1 plus a zero vector in S2, or zero vector in S1 and plus that vector in S2. So in other words, you have the non-unique representation of a vector. That's not possible. That's not possible according to the definition of direct sum. So in other words, okay, this implies that the left side and the right side must both be zero. Okay, left side, right side, this part must both be zero. But if that's the case, remember, because the UIs are bases, right? So they are independent. The only possibility for them to be zeros would be A1 equal to A2 equal to A blah, 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 equal to AK to be zero. Same thing applies to the other side, okay? Because V1, V2, blah, blah, Vn, they are bases for B2. For this linear combination to be zero, the only possibility is B1 equal to B2 equal to blah, 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 equal to Bn to be zero. Because all this, when I say zero equal to this one, I mean, I can derive that this AI, this BI are all zero. So what does that mean? That means this U1, U2, blah, 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 and the V1, V2, blah, blah, blah. The combination of all these two bases, combination of these two bases is linearly independent. So you have like this combination of bases. First, this combination of bases span V. Second, this combination of bases are linearly independent. So, in other words, you know, the only possibility is this one. Dimension S1 plus dimension S2 equal to N. Okay, it's not an easy proof. Okay, it's actually not an easy proof, but just want you to get an idea what it is. So let's continue. So the subspace S1, S2 of Rn are orthogonal if V1 dot V2 is 0 for all V1 in S1, V2 in S2. Okay. I mean, there are obviously like very easy examples. For example, in R3, okay, if the E1, E2 spans S1 and E3 spans S2, obviously any vector in S1 and any vector in S2, they are orthogonal, right? Not only that, okay, if S is a subspace for Rn, we can what happens? Actually, you know, we can, you know, sort of like for any basis, we can derive like orthogonal basis. Okay, I'll tell you about that later. Okay, so if S is a subspace of Rn, then the orthogonal complement of S is a set. You know, we say S, you know, orthogonal equal to U, all the U in Rn, such that U dot V is 0 for all V in S. Okay, this is definition, so nothing to be worried about. So if S is a subspace, then S, you know, orthogonal is a subspace as well. So how to show something is a subspace? Okay, first you need to show it's non-empty, right? So S, you know, is a subspace. So S has 0 vector, right? So obviously the 0 vector belongs to S orthogonal too. Okay, because uh, the 0 vector dot any vector in S must be 0. So 0 vector belong to S orthogonal too. And the second, okay, if S is a subspace, we have like if V in S, we can derive AV U plus V is UV in S. U plus V in S. That's subspace, right? So here, if U prime V prime in let me use S prime as S orthogonal. Sorry, I just cannot type it. So we can derive, okay, U prime plus V prime we need to derive this, right? This is what we need to do. So let me write it here first. So in order to show that, we need to show U prime plus V prime, okay, dot V, okay, equal to 0, okay, for any B in S. This is what we need to show, right? But we know like the U prime plus V prime dot V will be the same as U prime dot V plus V prime dot V, right? And because we already know like U and the V, U prime, V prime, they are already in S orthogonal. So this will be 0 plus 0. So it'll be 0. Okay, so we have our case. Okay. So then we want to find the orthogonal complement of the column space. Okay. So basically, so we have these two vector, column vector. This one, 1, 2, 1, 0, and the 0, 0, 0, 1, right? So basically, what we need is well, you can sort of like write it as like you know, a linear equation, the system of linear equations. Let me. So what we want is A, B, C, D, the transpose. Okay. Okay. This one dot. This one. So this one inner product. This one inner product. This the second the first column inner product. The second column both will have to be 0. So we know like A plus 2B plus C equal to 0. And also we have like D equal to 0. Okay. So having say that, okay, we know like if we let the A to be T, then it's going to be T negative 2T and the T, sorry, if we let the A to be T, B to be S, so TS and the C will be negative T minus 2S, okay, and 0. Okay, so this contains all the possible solutions. So we try to separate this one into the terms for T and terms for S. It will be T times 1, 0, -1, 0, plus S times 0, 1, -2, 0. Okay. So in other words, 1, 0, -1, 1, 0, -1, 0, and the 0, 1, -2, 0. These two vectors span the orthogonal complement of the current space A. Okay. So let S be a subspace of Rn, then Rn equal to S direct sum S orthogonal. Okay. And dimension S plus dimension S orthogonal equal to N. And the S orthogonal and orthogonal again is S. Okay. So the proof is kind of straightforward. Okay. So let W1, W2 to WK be the orthogonal basis of S. Okay. So for any vector in Rn, okay, we let V1 to be this one. Okay. It's a linear combination of WK. Okay, but it's like a V1 in a like a what should I say? Like a it's a V1's projection onto W1. Okay, it's a V's projection onto. So what should I say? You can see like we pick any vector V in Rn, right? And here, okay, the first term, you see this is exactly this one, right? We try to calculate the projection. We try to project the V onto the W1, right? This one. If you still remember what we covered for the projection. So this is the projection of V onto W1. This is projection of V onto W2. This projection of V onto WK. Okay, so we try to, project the V onto the basis of W1, W2, blah, blah, to WK. Okay. And remember, W1 to WK is an orthogonal basis. So first, like, you know, the inner product of any pair of them is 0, okay, because they are orthogonals first. Okay, I forgot to mention about that. Okay, and now okay, this is a V1. And V2, okay, we let V2 to be V minus V1. Okay. Obviously, V equal to V1 plus V2, right? Okay. And V1, okay, because it's like a linear combination of WKs. So V1 must be in S. And we can easily show that V2 is in S like orthogonal. Why? Because, if you try to, you know, uh, um, V2, okay, you try to do like any product of V2 for any WK. Let me just do one. So, for example, let me just use W1. Okay, dot V2. It's going to be, W1. You can see the it's going to be W1 dot V2 is V minus V1, right? Right? So it's going to be W1 dot V, okay, minus, okay, W1 dot V1, right? So what is V1? V1 is all these things, right? But as I told you earlier, this Wi, they are orthogonal to each other, right? So you don't need to worry about the second term, third term, and so on. So on. For V1, for V1. Because W1 dot V2 is 0. W1 dot V3 is 0. W1 dot VK W2. W1 dot W2 is 0. W1 dot W3 is 0. W1 dot WK is 0. So all these second, third, fourth, all the remaining terms become 0. So it'll be minus this V dot W1, okay, divided by W1 dot W1 is basically W1 squared, right? Dot W. Is a W1. V dot W1. Okay. So you can see this one is W squared, right? W1 squared. So this one and the denominator cancel out each other. So this one will become W1 dot V minus W1 dot V. So you'll be 0. Okay. So I just show you like, you know, V2 dot W1 is 0. You can check out V2 dot, inner product, any WI will be 0. Okay, so in other words, V2 is orthogonal to any of to a space that is spanned by this orthogonal basis. Okay, so V2 is in S orthogonal. Okay, so we here we show Rn is because we pick V to be any vector in Rn, right? So we are able to write V to be V1 plus V2. And V1 is in S, V2 is in S orthogonal. So Rn is the direct sum of S and S orthogonal. Okay. So we have the first point. For the second point, okay, we directly get it from the previous proof. This one. What happened? Orthogonal. This one. This one. We directly get it from here. Okay. For the third point, okay, you can show that W1, W2 is to WK, okay, it is the basis for S. It is also the basis for S orthogonal. Okay. I will leave this one for you, okay? Because the time is almost up, okay? So the last part is the projection, okay? You can project a vector to a subspace, okay? So let S be a subspace of Rn. So we know Rn equal to S direct, like a direct sum S orthogonal for any vector in Rn. So we have V equal to V1 plus V2 for some unique V1 in S and V2 in S orthogonal. The vector V1 is called the projection, projection of V onto the subspace S1, subspace S. We denote it as the V1 equal to PROJS V. Okay, this is a denotation. So if S1 V1 to VK be an orthonormal basis. So what is orthonormal? Orthonormal means like it's not only orthogonal, it's also like each vector is a unique vector. Okay. I mean, if you have an orthogonal basis, it's very easy for you to construct orthonormal basis. Basically, just divide like each basis by its length. So then the projection of V onto the S is this one. So if you look at here, you can see that it is sort of similar to what we are doing here. This is the V1, right? This is actually, this is exactly the V1 that we have written here previously. Okay. So it's just writing a little bit different. So I don't think I need to prove it again because it's basically the same as this one. And I already show you that, I mean, first, this is like in the space S, right? It's because it's the only difference is that, okay, you see why don't we have like denominator? That's because, remember, I told you, this is orthonormal basis. So because it's orthonormal, so like the size of each vector in the basis will be one, right? So the denominator here are all one. So you no longer need to write these denominators. That's why, okay, it is simplified to be something like this. Okay? And the the projection, if you have a projection, then you can define the distance. Okay, the distance would be, okay, V minus the projection. V minus projection, which is exactly what we have here. Basically, it's the V2. And we can show that this distance, or like well, the size of this is the smallest one. Okay, from V to any vector in U. Okay, but I think we are running out of time today. It's already like a 53. Okay, so I will finish this part next time. Okay, just less than just 2 slides. Okay, so yeah, like so next quiz will cover, okay, from whatever we didn't cover in the third quiz to well, this one is section 2. Okay, to section 2, okay, because we have like really plenty of time for this quiz, for you to prepare for this quiz. Okay, so I will give you like more material to prepare. Okay, I will upload the practice question to e-class. Okay, later today. Okay, and please, like remember, we don't have class next week and the week after next. I mean next week because I'm out of country. Okay, for conference. The week after next is because like it's a field day. Okay, 运动会. So we will have the quiz near the end of well, actually I will give you like one hour, okay, for the fourth quiz. Okay, so yeah, so it's going to be like you know November, I believe November 12th, right? November 12th. Okay, so any question? So if no question, I will see you, well, face to face. Okay, uh, on November 12th. Okay. Yeah, thank you.